general introduction to this webinar. My name is Andres de la Escosura. I'm coordinator of the CORENET project, a European initiative to try to deal with complex chemical reaction networks and to use them for a particular application, reservoir computing. So I will introduce shortly the consortium in a second. But basically, the purpose of this webinar was then to, let's say, to give some information to all our students, but also, of course, this is open to people external to the consortium about computational approaches to chemical networks. And this is the reason. Well, so basically, the relation with the project is obvious. So we're trying to implement reservoir computing on microfluidic chips using chemical reaction networks, and for this you need expertise from different fields, of course, reaction networks, metabolomics analysis, or algorithmic informatics, and also microfluidic technology. But of course, this is very much based on a computational approach, and this is what we are tackling today in this webinar. For that, we have prepared, I think, quite an interesting panel of speakers. So Christoph Flamm will talk about insights on computational chemical networks. So he's external to the consortium. We wanted, let's say, a different view, and I think he's a perfect fit for this. And then we have two young researchers from the consortium, Dr. Katja Sofia Sisi from IBM Research, who will talk about first principles exploration of chemical reaction networks, and Dr. Assis Gierig from the University of Southern Denmark, who will talk about in silico chemical reservoir computing. Just very quickly, some practical information. So the event is going to be recorded, and we may share some of the contents in the CORENET website. So I guess the speakers have already spoken with Miriam Frances. By the way, I would like to thank Miriam for the organization of the event. Anyway, if someone has any trouble with this, please contact her and let us know. And then there will be a questions and answers function. Please submit your questions there, and I will try to moderate and to involve everyone in the discussion. So with this, I will cut to the chase. I think the important people today are the speakers. So here they are, and I would like to say a few words about Professor Christoph Flamm. He's associate professor in the University of Vienna. He's quite well known for her work on systems chemistry, where he and his colleagues have proposed like a new approach based on graph theory towards chemical networks, which I think is quite novel, and is also or it can be very useful in this field. And therefore, for me, it's a pleasure to have Christoph Flamm here with us today. I know him since many years ago, and Christoph, the screen is yours then. So thank you and good luck.
Thank you. Thank you for the opportunity to. Oh, I can't share. You cannot share.
I stopped the sharing now. So
okay. So
in principle,
let me see. Now it should work. Share. Let me see. Oops. Here it is. Share. No. So now you should see my.
Yes.
Yeah. Okay. Perfect. So let me just. Okay, so thank you very much. So for the nice introduction and the opportunity to speak here. So let me start first to give you a little bit an overview where our modeling framework is situated. So if we look at the landscape basically of modeling approaches in chemistry, then from top to the bottom, so to say, it gets computationally less and less demanding. So on top, of course, we have the first principle methods, quantum mechanics, where basically we need a certain amount of assumptions to to arrive at something like the potential energy surface, right? And so there on that level we have electron densities, right? So the notion of a bond is not really existing, so you need additional pieces of theory to arrive from the densities at something like a bond concept, right? And the bond between atoms, right? But the theory is there, right? This is all you can do, right? But if you go a level down and then accept the fact that you have a concept like bonds, that atoms are connected via bonds, well, then you arrive basically in the realm of molecular dynamics, right? And you arrive at something like a reaction coordinate. You can, so to say, define conformational landscapes and things like that, right? And still, so to say, um, molecular dynamics is quite expensive, right? And so our approach goes deeper, right? So we, so to say, abstract three-dimensional space out of our molecules. So our molecules, as you can see below here, are edge and vertex labeled graphs, right? And then chemical transformations are usually, so to say, modeled as graph rewrite rules, where we have three pieces of information that you have usually from a chemical reaction, namely what is the pattern that you need to find before in the molecules such that you can apply the chemical reaction. And then there is the right-hand side R here, which is basically all the bonds and features which are there after the reaction, which were not there before the reaction. So this is basically our formalization levels. So our notion here is large hypergraphs, right? And of course, between all these levels of theory, and there are many, many more, right? There is a set of approximations, and you can switch levels depending on, so to say, on these approximations. So there is a way to work, so to say, results that we have up to the quantum mechanical level, which would require to embed our molecules in 3D space. So this is a computationally hard problem, but so to say, there are solutions to do that. And then, so to say, to investigate certain properties which we lost in our framework, then on a high level of theory. And so my view here is always use the right level of theory for your question, right? And then, so to say, you can switch levels. If you have found a phenomenon you want to study, well, then you can still switch between levels and then study various flavors in different levels of theory here, right? So let me come to properties of our graph-based formalism. So the central idea here is we wanted to have a formalism that preserves crucial properties of chemistry, and one you will see that mass conservation is one of the most critical properties that you need. So chemistry can't generate mass out of nothing, and it also can't destroy mass into nothing, right? So it's just basically mass is always conserved, right? Then if we look at chemistry, then chemistry has some kind of algebraic properties, right? So we have molecules, and molecules can react and can generate novel molecules, which themselves basically can give rise to totally new ways how the molecules can react, right? This is classically a feature of an algebra, right, where the objects and the operators basically work together hand in hand, so you can distinguish between object and operator in a certain sense, right? And the nice thing here is that if we view chemistry as such an algebraic object, then, so to say, it's relatively natural to make the transition from molecules via reactions to full reaction networks, because in the view of an algebra, this is just compositional terms. So molecules and reactions basically decompose into reaction networks, right? And Then on the level of the reaction networks, there are, of course, interesting properties we want to study. There are some topological features, namely finding certain patterns in these reaction networks. Then there are properties related to causality. And then, of course, there is also properties related to dynamics. So here we need to rely on first principle methods, because whenever we study dynamics, we of course need rates and energies of formation and these kind of things, which is of course out of our modeling framework, but we can parameterize, so to say, our methods then with more complicated ones. So I want to emphasize a little bit the causality topic here. So the causality is something which can be studied at our level of theory, which is lost, so to say, if you go up to higher levels of theory, right? So in our level, a reaction operator can only match if, so to say, the precondition is there. So we must find a particular pattern in our molecule, and if we find this pattern, then we can apply the rewrite rule and basically rewrite the molecule to the products, right? And that's exactly the way where the causality comes in, because we can now ask the question in a system where rules are applied, we can ask the question, um, what was the reaction that generated a particular precondition for another rule later to match, right? And in that way, we get causal chains of events in our formalism, which allows us to make a causal reasoning, which is lost on higher levels of theory. Right, and then there are some other properties, like we want to track atoms through our network. So we want to be able, if we have a reaction network, we want, so to say, to find out where does a particular atom that I feed into, or molecule, atoms from a molecule that I feed into the network ends up in my network. And as I said already, so I'm a big fan of, so to say, discover on the right level of theory and then refine your findings on a higher level of theory. So I want to first illustrate how so a static approach, right, that we use quite often. So what we have is we have our reaction operators, which is just formalized chemical reactions in terms of these rewrite rules. Then we have molecules, here these yellow dots on top, right? So these I can now apply rewrite rules to these molecules and can generate hypergraphs, large hypergraphs. There we have a strategy framework such that we can, so to say, circumvent combinatorial subspaces when we want to generate these huge chemical reaction networks. Well, and then once we have these chemical reaction networks, then if we want to look for patterns or for mechanisms in there, then, so to say, we translate our question to the network always into an integer hyperflow problem. So what we want to do is we want to feed matter on one end into the network and then find, and so to say, drain it on somewhere else, right? And that we can then solve with an ordinary optimization problem, right? Which gives us a lot of freedom. Namely, we can factor in thermodynamic properties, structural properties, whatever. So how we define what is now optimality in our terms, this can be, so to say, tuned. And that's the reason why it's nice, so to say, to have such an optimization framework to find, for instance, pathways. So pathway is the easiest problem. So there I have input into my network on one side, and so to say my product on the other side, and then I can ask the question, does a pathway exist there? How does the shortest pathway, how does the most optimal pathway in terms of atom economy look like, and whatever. So these are questions we can investigate on this static network. So let me illustrate it on a quite unusual space. So of course, we can not only construct huge spaces, we can also take a molecule and deconstruct it with our chemistry into, so to say, building blocks, right? And then investigate the deconstruction space. And I've picked here an interesting class of molecules, namely polyketides, which is the most versatile group of molecules that we know, right? So in a sense, it's a polymer of acetate units, but you have various complicated ways how to modify them later, how to cyclize them. So it gives rise to a very, very, very rich, so to say, repertoire of scaffolds, right? And so in nature, of course, you have some complicated polyprotein, which is analog to some kind of an assembly line, and so the growing molecule is handed over to the next processing place, which is here symbolized by these colored squares, right? And then in the end, so to say, you have your polyketide, and then so to say, you can still, so to say, modify certain parts and change the molecule. And that's the reason for this for the niceness of this class. Okay, so what we can do now is we can take this chemistry, which, so to say, is formalized in these polyketide synthetases, right, and apply it to a polyketide, the yellow one here, right? And then just deconstruct and see how does the construction space look like, right? And so we did that, and then we, of course, can pose a flow query. We can ask, how is this polyketide constructed from building blocks that arrive, so to say, during deconstruction, right? So basically, we have the question, we have one polyketide, and then we have these SH units where the partial molecule is handed over, and so since it's using Gleisen condensation, we also generated 5 CO2 molecules while we built the molecule, right? And then we want to ask the question from the original building blocks, which is a acetyl-CoA unit, right? And malonyl-CoA unit. So how is this molecule generated? And then we find out, well, there is 2 ways, right, to construct this molecule, which is however stunning, right? Because it's basically a linear polymer which then cyclizes, and the question is, how do 2 different construction pathways arise here? So as you can see here, the lower part, how, so to say, the polypeptide chain, the polyacetate chain is, polyketide chain is formed, is basically the same for the 2 pathways, and then in the last 2 steps, so to say, something seems to be different. And here the strength of our approach comes in, because we can now track atoms, individual atoms, through these flow solutions or through the network that we have. And so if we now label our polyketide chain at atom number 1, which is symbolized in the upper and the lower part here by this black dot that we have here, well, then we can follow, so to say, this atom through the construction steps, right? And then it turns out that we indeed get two different positions in our final molecule, which is of course the same molecule, right? Where, so to say, our isotope label ends up in 2 different non-isomorphic positions, right? So there's really, so to say, a difference here, and you can see it. These polyketides have a very rich way of folding, right? And so to say, the red pathway basically first closes the C3C8 bond to form the first cycle, and then the 110 bond is closed to produce the second cycle, while the first pathway, the cyan one, first closes the 2,7 bond, which is a different one, right? And then, so to say, the 110 bond, which is also a different one in the final molecule. You can see that here by these highlighted bonds here, right? And in that way, you can now understand how a particular molecule is constructed. And it turns out that the biologists really found 2 organisms where one organism, so to say, constructs the molecule according to the red pathway, and the other organism according to the cyan pathway. And so you wouldn't have recognized that if you don't have the ability, so to say, to track atoms through your reaction network, because the final molecule, of course, is the same, right? Okay, so this brings me to more complex patterns. So finding pathways is a relatively easy task, right? So another very interesting task for us is to find a pattern that's termed autocatalysis, right? And autocatalysis was ill-defined when we looked at the problem, right? It was more or less, so to say, a kinetic phenomenon. So the people you see that on the left-hand side here described these sigmoidal curves here, where you have some kind of a lag phase in the beginning, then you have an exponential growth phase, and then in the end, when the food runs out, then you have this saturation phase here. If you look at the phenomenon from chemistry, then you get things like basically two processes, a very slow process that generates the autocatalyst from the food molecule somehow, right? And then you have a catalyzed version, which is fast. Then once enough catalyst is there, where the food is transformed by the catalyst into a second copy of the food, right? And so the question is now, how would you find such a pattern? And you can, of course, formalize now this question: is there autocatalysis in a reaction network as a flow query, and can look for autocatalysis. Recently, however, Philippe Nguyen and Alex Blockhuis in Paris, so they made a stoichiometric formulation of what autocatalysis is. And this is depicted down here. So this is, in a sense, a catalytic cycle which has an ear, so a parallel pathway, and the ear is connected to the catalytic cycle always in a split-off reaction, right? And then you have a merge point, a species where, so to say, the alternative pathway merges back into the catalytic cycle, which then produces basically two copies of the network. And so they basically devised a framework how to classify autocatalytic reactions. And the classification you see here on the right-hand side. So you have 5 types of autocatalytic subnetworks in principle, right? So for the first 3 types, we know instances, real chemical instances. For type 4 and type 5, no instances known, so up to now. And so this framework helped to classify this zoo of autocatalytic reactions, which were first only characterized by a kinetic phenomenon, into a structural phenomenon where we now can say, okay, this autocatalytic reaction is of type 2 or of type 3 or type 1. So we have a classification scheme here now. However, the problem still is we need to find these guys, right? And the question is, why are we interested in autocatalysis? Well, autocatalysis is a source of nonlinear dynamics in networks, which is interesting to know if we have a chemistry where something like this is in there, right? And here the problem comes, we first need to find, is there a potential autocatalytic subnetwork in my network? I have to identify it, and once I have identified it, I can then study it, so to say, with more fine-grained methods, if it, so to say, really meets also the kinetic criteria for autocatalysis. But first of all, you need to identify these things. In networks, autocatalysis can have a canalizing, can canalize matter, right? So here you see an example. So this is the glyoxylate scenario from Eschenmoser, where he, so to say, hypothesized, so to say, a way to come from cyanide to all the building blocks you need in metabolism, right? And what you see here is you have polymerization chemistry on the left-hand side of HCN, right? And this is, of course, a huge reversible network. So you start with HCN, and then so the matter is dispersed over a huge network, right? However, once later, then, so to say, glyoxylate is generated, and glyoxylate can autocatalytically convert basically the dimer into another copy of the glyoxylate, which now allows the autocatalytic reaction basically to suck back all the dispersed matter over the network into a single component, right? This is a very useful phenomenon that you can have, right? And therefore, of course, we are interested. And then finally, the other question is how frequent is actually autocatalysis? And for that one, we need to look at random instances of networks, right? Question is, are there different types of chemistry which harbor a lot or which harbor no autocatalytic subnetworks, right? So this brings us basically to the question: is there a random network theory out there for chemical reaction networks? And then, if you look, you find there's mathematical network models out there. So the idea behind those is to provide a null model such that you can find statistic significant features in random instances compared to real instances that you see, and then to get, so to say, insights from the construction rules of the network on the feature that you observe, right? And the most common ones are Erdős-Rene models, Watts-Strogatz and Barabashi-Alberts model, which generate different networks, different mathematical networks with certain properties like small world or local clustering or whatever, right? The basic assumption here, however, is that every node can reconnect to every other node. So every node can interact with every other node. And this is exactly where these models break the chemistry, because in chemistry, not every molecule can react with every other molecule. So it's a very huge asymmetry in there. So we need basically a different approach to randomize networks. So what can you do here in that regard? Well, you first have to decide, do you want to randomize the structure of the network, right? How the molecules are connected, or do you want to randomize the chemistry itself, right? Because you could introduce other chemical reactions, right, that make the molecules, which would be a randomization on the reaction operators and not on the structure, so to say, of the network. If we do that, then we can ask two questions. So is every network that we generate with these strategies a chemical network? And the answer to that one is no. It's only a chemical network if we have mass balance in the network. Without mass balance, we get unchemical networks. And then the related question is every hypergraph that a person gives you a chemical reaction network? And here also the answer is no. So also here the network must be conservative, so it must be mass preserving, so which means basically that in the stoichiometric matrix of the network, you must find in the left null space a strict positive vector. If you don't have that, then your hypergraph, as nice as it looks, is not a chemical, not describing a chemical reaction space, right? So these are two useful conditions. So we can go back to how do you randomize now chemical reaction networks? Well, the first thing is you need to preserve mass. This is essential. If you don't do that, then you go away from your from your chemical network instances. Well, and then we can look basically at what are the features of a chemical reaction, right? And there are three crucial features. We have sideness, role, and arity. So with arity, I mean how many educts and how many go into a reaction, how many products come out of a reaction, right? We can have many to many or one to many or many to one reactions, right? With the sideness, I mean, so we have an educt on the product side, and of course, by rewiring, we can switch that, right? And the role change is does an educt become a product and vice versa, right? And here I show you two chemical reactions and a randomization strategy. So the first one basically just switches the products here, right? So mass is preserved, of course, right? arity is preserved, right? And same number of educts go into the reactions and the same number of products come out of the reaction. And the sidedness is also preserved because educt molecules remain educt molecules, product molecules remain product molecules. However, there could be another randomization strategy as shown down here, where we don't preserve none of these features, right? So here we rewired our chemistry in such a way that that, so to say, some of the educt molecules became product molecules now here, and some of the product molecules became educt molecules, and also the arity, so to the number of educts and products per reaction changed. And that's the big question. So there are many randomization strategy, and the question is, what do you want to preserve from these properties? And if you think about it, then there is a huge set of 25 randomization operators, and we implemented all of them and have a very nice random model for chemistry now, where we can then ask the question, basically, given a chemical reaction network with a certain density of autocatalytic subnetworks in there, how is that distributed in randomized networks? So is it really a statistically significant feature that we see here in that chemistry, or is it just a chance event here? Okay, so if I have time, let me come to the last aspect here. What I showed you is always the assumption that we can generate the network. However, there's a lot of chemistry out there, which is what I would term a combinatorial space. So if I have polymerization chemistry like the HCN one or other ones, then I can have a combinatorial number of species, and then it's of course not possible to generate enough of the reaction network to make decent conclusions of which patterns do you find in there. So the question is, can we still do something here in our rule-based realm that we have? And yes, we can do something. So what we need is basically our reaction operators, and in that case we need rates. So we need, so to say, a formal, we need to get the rates from somewhere, and the thermodynamic, so the energies of formations of our molecules, right? And then we need, so to say, a certain event that happens. Let's say I have HCN chemistry running, and suddenly adenine is produced in my reaction soup, right? And now I want to know, how is this adenine generated in this dynamical system from my building blocks HCN, right? And for that one, now I can make a Gillespie simulation, the stochastic simulation, right, which, so to say, simulates the system physically correct, right, and generate trajectories. And in these trajectories, I can always memorize how was my reaction, the left-hand side of my reaction rule embedded in my reaction mixture. So up here, you see a reaction rule, the left-hand side, which reacts, so to say, to that dimer here on the right-hand side. And then down here, the blue rectangle here is my reaction mixture, only with 3 HCNs in that case. However, you see that I can have two different embeddings of which of the molecules and how do they react to generate, so to say, the product molecules. So if I remember at which time point which reaction rule was applied in the reaction mixture, then with the causality that I told you, I get a handle on regenerating from the event of interest what, so to say, what the events were that happened in my concurrent system and resulted, let's say, in the adenine production here, right? So the point here is that in this event simulation, of course, the molecules don't know what the mechanism is to generate adenine. Many events happen in parallel. Some events contribute to the production of adenine, others not. But since we have this causality notion in our formalism, we can backtrack then from the final results where we know which atoms ended up in the adenine, we can, so to say, backtrack through the set of events into and reconstruct from trajectories the mechanism. And this works in that way that, so to say, I take the last reaction which produced the event of interest, which is 5 in that case, and then I ask the question, what was the reaction upstream in time, right, that generated the proper preconditions such that the last reaction rule could happen, right? And so I go back and then I find this reaction, everything in between, so to say, I can, so to say, splice out of my trajectory. And in that way, I can compress, so to say, this huge stack of reaction events into, so to say, a proper mechanism, right? And so this allows us now to identify how is a particular molecule given a certain certain reaction operators and dynamics, how is a particular molecule generated in this reaction mixture, which is a very useful type of way how to reason about these things. I also want to mention that, of course, we can identify with this mechanism also feedbacks in the system, so self-limitations in the dynamics of the system, which is very important, because then we can better understand, so to say, how so to say the interaction of reaction rules lead to the final event, which allows us then to be more fine-grained if you want to design a system that behaves according to a certain mechanism.
Christoph, you
Yeah,
are.
that's it. This is my last slide. So this is my conclusion slide here. So I hope I showed you that, so to say, you need at least a formalism which is expressive enough, shows properties of chemistry. A graph approach seems to be the right level of abstraction here to find patterns and to find these things. And of course, we can take combinatorial spaces with this method. And most important, we can also, so to say, apply the problem to open systems, namely to systems where matter flows into our reaction vessel and flow out of our reaction vessel without changing much. Okay, this was my presentation, and yeah, I'm up for questions, or do we move on and have the questions in the end? So
We are a little bit behind.
Sorry.
Good, but no problem. So I would not like to close your contribution without a question. So is there any question from the audience? Here I can see. So Thijs de Jong from Radboud University in Nijmegen asks, well, thank you for your for the interesting talk. Finding the causal structure or searching for feedback sounds like you have to run to all possibilities parts. Is this computationally expensive? How well does it scale to larger networks?
Well, the most expensive part is, of course, the physical simulation of the system, right? So you need to accumulate enough trajectories to find. So one trajectory is not enough. So you need to a statistically representative sample. So there is a certain limitation in the size of the system. So it can't be too large, right? But for typical systems that you find in systems chemistry, it should be fine enough, right? For these, you can do this type of analysis.